When we design instructional video, the instinct is to mimic high-end modern media. We aim for a seamless, polished presentation flowing continuously without interruption. Take Sergio, a subject matter expert tasked with teaching a 5-step procedure for designing relational databases. His instinct is to record a single, continuous video demonstrating all 5 steps sequentially. His instructional designer, Reshmi, completely disagrees. She proposes breaking that continuous timeline into separate, fragmented blocks and forcing the learner to physically click a button before advancing to the next step. This table compares their two approaches. Sergio's outline on the left groups the procedure into one linear block. Reshmi's outline on the right severs that flow, breaking it into distinct units with pauses and practice exercises inserted. Experts routinely default to Sergio's model. Because their brains have already mastered the material, they no longer experience the content as highly complex. To an expert, a continuous presentation feels like a clear, high-level summary. But an aesthetic, seamless playback experience actively works against the biological constraints of a novice learner's brain. The human cognitive system operates under rigid biological limits. When instruction ignores those limits, it triggers a failure state known as essential overload. The first constraint is the hard capacity limit of working memory. A learner can hold about 3 or 4 distinct pieces of novel information. The second constraint is the duration limit. If not actively processed, they evaporate from working memory in roughly 20 seconds. When presenting a fast-paced, continuous video filled with dense, interrelated facts, you force data into that limited buffer faster than the brain can process it. The slots fill instantly, and older data is overwritten before it can be encoded. The biological hardware simply drops the incoming information. The learner becomes incapable of linking the concepts together and fails to build a causal mental model. To see how quickly this system fails, look at an instructional module explaining how lightning forms. It serves as an excellent proxy for any fast-moving, technically complex multimedia lesson. These storyboard frames show a 2.5-minute continuous animation of the lightning process. In that brief window, a novice is hit with a rapid stream of interrelated variables: warm air, cold air, updrafts, positive particles, negative particles, and stepped leaders. Because the video does not stop, the data is transient. If a learner fails to encode a single fleeting detail, like the fact that the top of the cloud sits above the freezing line, the entire causal chain of events that follows becomes entirely incomprehensible. We mitigate this biological bottleneck using the segmenting principle. Segmenting physically severs the continuous timeline of a video. It transfers pacing control away from the media player and assigns it directly to the person watching. Looking at a single frame from the segmented version of the lightning lesson, you can see the intervention. The animation plays a short 10-second clip demonstrating exactly one causal step, and then it stops. The learner must press the continue button to proceed. That physical pause gives the learner's working memory the time it requires to process and consolidate the current link in the chain before requesting the next batch of data. In a meta-analysis of 14 experiments testing this mechanism, allowing learners to control the pace through isolated segments produced a median effect size of 0.60. Introducing deliberate friction directly increases a learner's ability to retain and transfer complex information. This strategy is equally necessary in text-heavy, synchronous environments. This image on the left shows an unsegmented presentation slide from a geography course. It demands that a novice simultaneously read paragraphs of text while interpreting multiple spatial rules and grid diagrams. The result is instant visual overload. The segmenting solution for static graphics is the overlay technique. By progressively revealing the chronological steps of the concept one layer at a time, we prevent the user's working memory from being overwhelmed by simultaneous inputs. However, segmenting has strict boundaries. How you deliver the narration over these segmented graphics heavily dictates whether the learner actually retains the material. This is a dense, text-heavy slide from an experiment testing how students learn to calculate gradient ratios on contour maps. Researchers tested versions of this dense material using on-screen text versus spoken audio. They found that for highly complex verbal explanations, text outperformed audio. Spoken words are transient. If an audio narration exceeds 10 to 15 seconds, the first words spoken evaporate from working memory before the sentence concludes. Written text remains on the screen, allowing the learner to read and reread the logic at their biological pace. Segmenting requires precisely controlling both the visual volume on the screen and the auditory density hitting the ear. Even with perfect pacing, a learner's cognitive capacity will collapse if they are forced to decipher new vocabulary while simultaneously tracking a dynamic, moving procedure. Take a look at these two frames from an animation demonstrating how a car's braking system operates. As the animation plays, the voiceover explains that the piston in the master cylinder moves forward. To process that sentence, the learner must scan the diagram to locate the master cylinder, infer the definition of a piston, and track its physical effect on the brake shoes, all in real time. The essential processing demands exceed their mental bandwidth. The structural fix for this is the pre-training principle. Pre-training extracts the names, physical locations, and static characteristics of system components, and guarantees the user learns them before the main procedure ever begins. This diagram shows a pre-training interface. The user clicks on an isolated part, like the piston in the master cylinder, reads a brief definition, and observes its specific movement apart from the rest of the engine. This redistributes the essential processing. By establishing the vocabulary up front, the learner's working memory is entirely free to focus on the cause and effect chain when the full animation finally plays. This chart visualizes the outcome of the braking system experiments. Learners who received component pre-training before the main animation scored significantly higher on transfer tests, yielding a massive 0.90 effect size. Isolated prior knowledge of the pieces is a strict biological prerequisite for understanding the movement of the whole. Bringing this back to our initial design dilemma. Sergio's plan to package the database course into a single, seamless video ignores how the human brain processes novel data. It mathematically guarantees essential overload for his students. Reshmi's outline works because her design bends to the constraints of human working memory, structurally enforcing the pauses necessary for comprehension. We can translate these cognitive boundaries into a three-part checklist for instructional design. First, cut continuous timelines into isolated segments, requiring learners to physically trigger the progression. Second, progressively reveal static complexity. Use overlays to build dense charts layer by layer. Third, extract new technical terms from the dynamic procedure, teaching them in isolated pre-training modules. We cannot expand the physical capacity or duration of human working memory. Our only lever is tightly regulating the volume and speed of incoming data. The mark of well-engineered instruction is not a timeline that plays without stopping. It is the deliberate, strategic use of friction exactly where the brain needs time to build understanding.